Okay, folks, we're starting now a new chapter, chapter 8. And what we're going to be looking at is friction. And it's a little bit different. We have to be a little careful with the forces. The old standard rule that if you choose a direction and the sign will correct you doesn't always apply in friction. So we have to be a little careful about that. We need to think about what directions to choose those friction forces. We'll be constructing free body diagrams with these friction forces. So free body diagrams will be continually joining us, and then we'll be using equilibrium equations to solve for certain things in those. And then there's different ways of expressing friction too, coefficient of friction. And then there's also angle of friction. The geotechs and stuff tend to like that one better. But the angle of friction is also very nice too, because we'll find that we can oftentimes use a force triangle to solve the problem instead of going to equilibrium equations. And that angle becomes important in terms of one of those internal angles that, remember, we have to calculate via sines. Law of sines or law of cosines. So homework 13 is posted. I'm going to run over things.
What chapter do we go up to?
Huh?
What chapter are we going up to? What's the highest chapter that we're doing?
Oh, you mean in the whole class?
Yeah.
I'm trying to decide whether you're talking about the quiz or what. We'll do chapter 9 also. So friction and then moments of inertia, basically. I don't have my little string here anymore. So we'll be doing chapter 9 then, a little bit. But we're not going to be doing all of 4 or all of 8, and we're not going to be doing all of 9 either. So I'll show you what sections that we get into.
Will we be having a homework assignment over Dead Week?
No. Dead week basically is, supposed to be review week. So there may be something due like on the Tuesday or something that you have to bring in, but I want to make sure you get all of the moment of inertia problems done. Mm-hmm.
Have you ever done take-home finals?
I've taken them, yes. Let's just say when I got my PhD, I took one home and it took me 3 days to solve. So you may not want that, because you have to make it a little harder. But no, I've never given any. Darn. Any other questions? Okay, we'll talk a little bit about the theory of friction. And again, I always get thirsty when I put that up, but chapters 8, sections 1 through 4 is what we'll be looking at. Just so you know, there's other names, other books will call it different things. Coulomb friction, dry friction. Basically the same thing, the thing we'll be talking about here. Okay, so let's consider a couple of bodies in contact here. In this particular case, it's the floor and maybe a book or something like that. And we start to push on it. Now, our experience is when we start pushing on it, it doesn't always just move right away unless it's sitting on ice or something like that. So it takes a little bit of effort to get that to happen. What's going on is when we look at the microscopic level, this smooth surface isn't really so smooth. It's kind of bumpy. And then the floor itself might be bumpy. And at those points of contact, then, it keeps the body from basically falling through. So those are just simply due to the weight of the body itself, and actually I don't have that on there. So it's pushing down. And then we'll pick another cool color here. And then at those places where they're interlocking, what we're going to find then is there's a resistance, or a force, basically a horizontal force being pushed along there. And they're being resisted by per Newton's third law, equal and opposite, basically a set of forces like so. Or we can represent them as single resultants. So what we're going to see here then is a set of forces resisting it from falling through, but a set of forces then also from that interlock saying, I'm going to resist your pushing me for a little while. Did you bring enough to share with everybody? And we're going to find a set of forces then that the surface is going to be providing back at some point in time that says I'm not going to allow that movement. Now what we're going to do via statics so we love these equivalent forces. And again, statics, we need to get things into vectors. So we're going to create this equivalent friction force F. And we do a free body diagram of the box there. We've got our P and our weight. And then we're going to create this equivalent force, F, which now will have a direction because it's going to be basically, it's parallel to those where the two surfaces meet. Okay, so that's tangent to the surfaces, and then we're going to have this N and it's going to be perpendicular. So again, like we did with beams, remember we broke things up into shear and axial forces there. We tend to break things up into these perpendicular and parallel because what we're going to see is that the behavior is going to be a little bit different. So we'll talk about the friction behavior and what is actually going on in terms of this graph here. So it'll be plotting this force, friction force here versus P here. So we're basically referring to this free body diagram here again. And what we'll find is for a period of time, they're equal. As I start pushing on it, it's not moving, so the force, in terms of Newton's law, has to be the same. So it's basically pushing back at that P, but at some point in time then, what we'll find then is that we reach some maximum value, and your author uses Fm. A lot of other authors use Fs, and I'll show you why in just a second here. And then at that point in time, what happens is as things drop off, and it starts moving. But once it starts moving, we still have to apply some force to keep it moving. But we'll see that that force is generally less than what it takes to basically get it started. So in this section, there's no motion. It's just basically the forces are equal to each other. You're pushing and pushing, pushing. The friction force is pushing back, saying I'm not going anywhere. And what we call this is static friction. In this section here, then, once it gets past that bump there, we start having motion there. But again, there's still some friction force there that we have to overcome to keep it moving at a constant velocity. First case is pretty obvious, but we'll talk about the various cases. Question?
What's the FM? What's the M?
That's this point up here, this point where once we reach that point, then it starts moving. And then when it starts moving, it drops down to Fk and basically starts moving at a constant velocity. If we keep that Fk on it, it'll just move right along.
So is it FS on the left? Or is it still going to the
This is just
in the line of that first?
this.
Yeah.
Yeah, so this is just basically telling me that this is a one-to-one. That as I increase my P, that my F has to increase by that same amount. So if I put 10 pounds on it this way, it's going to give me 10 pounds back, and it's not going to move. And this is what this case is, actually. P is less than Fm. Oops. And that's what this case is simply describing there. It's just in this range here, say 10 pounds, I'm pushing 10 pounds on it. F has to be 10 pounds to keep it from moving. So that it's stuck there, the friction is holding it in place, that friction force is holding it in place, it's not going anywhere. But it's a function of this line now. So if I put on 10 pounds, it'll be 10 pounds. If I put on 1 pound, it'll be 1 pound. But there will be some point where basically it'll break free. That'll be our third case. So right at that point, right before what we call motion impending, right before it's ready to move there, that force will be equal to that one, just like that one, except that we've reached that particular point. Once we get then to motion, once we pass that point, Once we get past that, then the thing starts moving. And what we find is this is only a temporary thing. Because once it starts moving, it's going to drop down. So when we think about that in terms of the microscopic level, what happens is this kind of lifts off of the surface and then basically starts connecting with the surface, but at fewer contact points there.
We call that kinematic friction.
Kinematic friction, yeah. So that's what when we design a ski slope, we're going to be looking at a kinematic friction or ice skating and that sort of thing. That's the sort of friction that's basically the force that's necessary to keep moving at a constant velocity. Now we've got a couple of laws of friction that are some of them are a bit counterintuitive, so we'll have to think about them a little bit there. But the most important one what we'll find then is that this friction force is proportional to the normal force. So what we're saying then is then if we have a bigger normal force, a bigger force acting between that perpendicular between the planes there, then what we're going to see is that the friction force, that Fm, that maximum value that we have to attain to start motion, is going to be bigger. It's also a little bit tricky too, because when we get into reviewing this case again, when we're perpendicular, we're flat, basically looking at a flat surface there, and we set up our coordinate system such as this. What we'll find is that n is equal to w, pretty straightforward. We don't even have to solve for that. And what we find then is Fm is going to be some function of that normal force. So again, as it gets bigger, that force will get bigger. But the tricky thing is, green pen just does not want to work. Consider our force now, or our book being pushed up a plane now. So our P again will be parallel to that surface. But now W is still acting down. And the normal force, again, has to be perpendicular to that. And what we find is that the normal force is some sort of a combination of those two forces now. So think about, again, equilibrium. If I were to set up a coordinate system like okay, well, notice that P and W will have some component in that y direction. And what we're saying then is that normal force is going to be a function of those two in that direction there. But we have to establish that because then we can't, oops, wrong color. Since my friction force is now a function of that normal force is going to be different than this one here. So we're going to have to be a little careful in terms of how the forces are interacting. So if any of those forces have component in that perpendicular direction, we're going to have to account for that when we calculate this n. Once we get that n, then we can go back and calculate that force, that friction force necessary to get it to move. 2. This is one of those counterintuitive ones. What we find then is that this maximum friction force, this equivalent force, is independent of the contact size, contact area size. So it can be a little bit, a lot. It's going to be the same Fm that I need to overcome to get that thing to move. Last one's pretty straightforward, but the force necessary to get it to move is always going to be greater than the force to keep it moving. And we're not really talking dynamics here either, too, so there's no inertia involved in this. We're talking moving at a constant velocity. Okay, now we'll talk about the different ways of expressing this friction. And the first one we'll talk about is what we call the coefficient of friction. And that coefficient of friction is the Greek letter mu. So think of a French cow or something, mu. So it's mu of s times that friction, or that normal force. So remember we said it was a function of that. What basically we describe that friction is a function of that normal force there. And again, you'll see a lot of authors, instead of using Fm like ours do, or our group does, a lot of other books will use F of s there, because this is the mu of s. He uses the mu of s, which is static coefficient of friction. And but your author uses Fm, so we'll just stick with that. And then we also have one for the kinematic. And to calculate that, it's just simply going to be that friction force over that normal force. But again, this is where we see now, this is the relationship of our friction force. And think about it in terms of n. As n gets bigger, then the force necessary to get that thing to move, that maximum force to start pushing it there, to start it moving, basically gets bigger. As it gets smaller, it gets smaller. So it's a function of that, direct function of that n. Question? Mm-hmm.
The third law of friction, we're talking about having more points of contact than static friction, is that what you're saying? That's why.
What now? I didn't.
About why the maximum static friction is greater than kinetic friction. Were you talking about something about points of contact, or is that something else?
Yeah, physically what goes on is that when they're down, they're interlocking much closer and stuff. When you start moving, they actually it kind of raises up as it starts moving. It starts breaking off some of those points of contact and stuff like that. So there's a little less in terms of microscopically what's going on. But in terms of what we're concerned about, just think about it, it will always be a little bit less. one expression for friction. And we're using all sorts of Greek letters here, or Greek letters here. The angle of friction basically so what it is just simply that angle created with respect to n, so that's my cute little shorthand there, with respect to n, of the resultant force created by n and f. What we'll find is that n and f basically occur at the same point. So basically it's a single force. We've broken it into the components because, again, we're treating them differently. Their behavior's a little bit different. But again, they end up being a single resultant. You'll see a lot of this motion impending. That means that take me up to the maximum there, and then I start moving. Where'd my red go? And that's what that angle is basically measuring there, is just saying, OK, I'm going to take those two, I'm going to combine them. And the angle of friction is just simply describing that angle with respect to the normal force there of how far that resultant force of n and fm, or n and f, whatever, moves over. And for a definition, it's just simply going to be that inverse tan relationship. But an interesting thing to point out is noting its relationship to the mu of s. Since Fm can be expressed in terms of mu of s, so what that says then, if you've got one, you got the other, basically. So if you've got mu of s, you can calculate that angle. If you've got the angle, you can calculate the coefficient of friction. So that's how they're interrelated.
Wait, that's just regular tangent or inverse? Just regular tangent?
That's tangent. If I want to get the angle, then I would inverse.
Yeah.
Do the inverse, right?
Yeah.
Good question. Come.
It's like a subscript S next to the U, or
Yes, this is an S.
that's for the static.
That's static. So when we say motion impending, that means you're pushing it up to that level, then motion's going to start just shortly after that. So that's basically taking it to the limit. We're going to take it up to that maximum point, then the thing starts moving. You're going to start singing again. And then we'll just think about those relationships then. When there's no motion, what we're saying then, it will be less So now this doesn't have an S on it, but anything less, we can still calculate an angle of friction that's going on there. F will be, in this particular case, equal to P. Oops. And the relationship basically holds for the kinematic friction there too. And what we'll see is this is going to be useful if we start solving problems with the force triangles. Basically, we see 1, 2, 3 forces here. I can calculate one of my angles. And usually these are going to be perpendicular to each other and that sort of thing. So we'll have some interior angles already calculated. OK, so that's basically the theory behind it. Now we need to figure out what it is we're going to be solving for. So again, we're in statics, so you're going to be drawing free body diagrams. Part of what we'll be doing here and as we saw when we rotated that thing up there, the key thing is that we need to get the right N. So we're going to resolve those forces into those parallel and perpendicular. Obviously, the parallel is going to be our friction force. The perpendicular is going to be our normal force there. But we're going to, depending on, and of course, there's going to be things at different angles and that sort of thing. So we're going to have to figure that out. The other tricky thing and the caveat is basically that we're going to choose that friction force, so it's going to be acting opposite to the motion, the impending motion. But you have to be very careful because it has to be relative to that other body. So we've got to think about the motion. We'll see things when they're stacked on top of each other. We're going to have to think about, OK, which way is it going relative to the body below it or the body above it and that sort of thing. OK, and then we've got basically, once we've got that established, there's 3 different categories that we'll be looking at. forces. Forgot. Okay, so our first category basically is going to be a situation where basically all of the forces and all of those coefficient of frictions between the various surfaces, and they might be different between the different surfaces, all of that's known. And basically all we want to do is determine the status. Is it moving? Is it not moving? Is it moving at a constant velocity? So what we'll do, 2.1a basically, is solve for the normal force and that friction, or the force that's being acted on there in the direction of the friction. And then what we're going to do is then calculate what that maximum friction force needs to be. Once we've calculated, or once we solve for n, then we can easily calculate this if we know the coefficient of friction in that particular surface. Okay, if we have the situation then, if F is less than that maximum force before it starts moving, that's in equilibrium then. It's not going anywhere, it's happy. If it's equal to that, then basically it's going to start moving. It's impending. And if we find that it's greater than that, basically it's not in equilibrium. We've got motion going on there. And then F should go back to, if we are talking about a constant velocity, it should go back to that kinematic friction. Okay, the other category is we might need to find out what that coefficient of friction is for a set of forces. And basically what I say is how long is it stuck? What is that range basically? And then basically it's just simply solving for that. So we'll figure out what that maximum force is. And basically we can use that then to say this is the level of friction I need for that to be able to resist this set of forces. Probably the most common one is you'll be saying, okay, what does it take to get this thing to move? So it'll be the motion impending case. We know the coefficients of friction. And basically, it's going to be find that force. What's that force I need to get that going? And of course, it's not going to be nice on a nice flat surface. It's going to be some weird angle and that sort of thing. So we're going to have to do some calculations. And again, we have to solve for that correct n. So we have to be very careful about making sure we've got all the forces that are acting in that particular direction covered. Oops, wrong. I'm looking at the wrong one. Oh, I'm sorry. I'm reading the wrong one here. Move this right above it. Same. This is probably the trickiest part of this particular thing, is that we're going to then have to assume a motion. Usually it's pretty easy. If the force is pushing one way, you're going to know it's going that way. And then the thing we have to be very careful of is then set that f of m in the opposite sense there. It will work if you set it in the other sense, but it won't give you the correct answer. So you need to be careful about making sure that's the correct sense. Then we solve for n, although actually you can do them out of order. And then what we're going to do is then go in and use our equilibrium equations and solve for that unknown force. Okay, so basically that's all of the written stuff. Now we'll just go ahead and start solving problems. And of course, like I say, nothing's going to be on a flat, nice flat surface for you. So we've got this block that's being a 45-pound block, basically. It's got a force being applied to the center there of P, which is going to be 40 degrees from the parallel line to that 30-degree incline that it's going up. Weird-looking block as far as I'm concerned. But and then we've got three things that we'll go through here. We might skip 8.4, just do 8.3 and 8.5, because there's another problem I want to show you there. But the block basically is asking when the friction force is equal to 100 pounds, whether the thing's in equilibrium or it's moving. And then case 8.5, well, 8.4 is the same thing. That's just a different value of P. And then finally, 8.5 is then the more interesting problem is okay, what's the smallest P necessary to get the block moving up the incline? Keep it moving. Well, that's going to be our constant, that mu of k there, that kinematic friction. And then the other interesting case is then to prevent it from moving down. So there's going to be a certain level of force there that's going to be necessary to keep it from sliding down. So we'll talk about those in terms of how to solve them via the categories that we just talked about. Okay, so the first one basically is saying I've got 100 pounds being pushed on that, and it's saying what's the status of that. So that's going to be that first category, basically. What's the status? Is it in equilibrium? Is it moving? So the first thing we do is draw our free body diagram. And this is that weird looking block. And what we'll do is we'll set up an equilibrium system. We'll set up our Cartesian system there, so it's going to be parallel to that plane, just to be a lot easier there in terms of summing forces in y and x and that sort of thing. So those are the two known forces. And then what I'm going to be interested in terms of solving a friction problem is I need that normal force, which is going to be now perpendicular to those surfaces. The other thing I need to think about in terms of motion is then which way am I going to go here? So we'll assume motion will be this way. Which implies then I'll draw my friction force opposite of that impending motion. So I'm thinking that 100 pounds is pretty heavy, especially if they're giving me one at 60. So this will be our case 2.1. Basically, is it in equilibrium? So the first thing I need to do is calculate my normal force, which is going to be a combination of things. So again, what we find is that we end up with a little bit of geometry here. We have to think about this. Okay, this used to be perpendicular here. If we consider this perpendicular here, what we can say then is that it's rotated 30 degrees basically to create this Cartesian system here that's parallel to this 30-degree surface here. So I've had to rotate that over 30 degrees. Then the 45 that's acting perpendicular to that surface now is going to be 45 times the cosine of that 30 degrees. And then we've also got this P, which is now 100. And we need to think about this one. Well, this has already been measured from the parallel there, so I can just go ahead. What I want is that perpendicular distance there. And we'll find that it's just simply the sine of that angle there. And then the missing piece then is my n. Go ahead and plug through that. And I carry the extra digits around because I'll have some interior calculations that I need to consider. Okay, so our next step is then, okay, let's figure out what this friction force is. I've got my normal force, but what is the force necessary right now with this force of 100 being applied to it? And what we're going to find then is it's basically the converse of all of that. So now I want the sine of that 30 degrees there, and the 45 basically will be acting in the positive sense. Think about basically constructing my force triangle like so. Then my P will be acting in an opposite sense. So that's just simply the cosine of that angle. That's a pretty easy one, but it'll be acting opposite of that sense there. And then my F, I've got shown in the positive direction there. And it comes out as a positive value, which means then, okay, in terms of equilibrium, it has to be acting that way. You have to be a little careful in your choosing of the direction there. Yeah, that you got to pick an impending motion. And the problem is then a lot of people, if there's 2 or 3 bodies moving, like stacked bodies and that sort of thing, and one's pulled this way and that way, you've got to think about, okay, what's the relative motion between those 2 surfaces, those 2 bodies and that sort of thing. So that's where you got to be a little careful on that. Okay, so we find that, and then part B, is simply that calculation. What is that maximum value that's necessary to do that? I've got my mu of s, which was given to me as 0.4. And when I calculate that, I come up with a value of 41.3. So what does that tell me? Blocks in motion. Basically, I've exceeded the maximum value there, because for that to be in equilibrium as it's sitting there right now, it has to be 54 pounds. But it says once I've achieved 41.3, it starts moving. So that won't be the case anymore. What we'll find then is that F has to be equal to mu of k if it's moving at a constant velocity. So if it is indeed moving, basically, it would have to be about 31. But basically, if it's a force of 100, the body started moving. We're not going anywhere. Or it's going somewhere. We can't stop it. It will be accelerating at that point in time, and then I'll let you deal with that in dynamics. Again, I'm going to skip 8.4 because it's pretty simple. I'll post it on the web if you want to see it.
You always calculate static first, and if that fails, then you have kinetic?
Yeah, well, you would use the kinetic if you were asked, what's necessary to keep it in motion.
Okay.
I mean, basically what we were given here is that it's 100 pounds. So if it's 100 pounds, the thing's moving. And we can't say anything about it. It's accelerating at that point in time, so we've got to do a different sort of calculation. If it did go to a constant velocity, then it would take basically about 31 pounds to keep it just sliding up.
Yeah, okay.
8.5 is a little more interesting. And we'll do the A part first. And again, this is going to be case 2.3. So what we're going to do is find that unknown force. We've been given basically a set of forces. We've been given the frictions and that sort of thing. What we want to do now is find those unknown forces necessary to get it moving somewhere. Free body doesn't really change much. Now for our first case, it's asking us to start the block moving up the incline. So basically in terms of if it's moving up the incline, my motion will be like this, which then implies I need to draw my friction force now in the opposite sense. So I know it's moving up. Friction force is going to resist that, so it's going to be pushing back on that. Oh, and I'm going to make sure I get my... So again, what we'll find is most of these are just kind of exercises in geometry, getting all those angles correct. OK, so my first step was then choosing an impending motion, basically, and then I choose my friction force in an opposite sense there. My step B, solve for n. Which we've already done, except that now we've got an unknown variable in here. So my p now is no longer 100. It's an unknown variable. It's the thing I'm looking for, really. Again, carrying those extra digits for precision. So I can describe my n in terms of this unknown variable, but it's still two unknowns. Oops, wrong one. OK, so my next step then is let's figure out what that maximum friction force is. What is that force necessary, basically, that Fm to start the motion? It needs to exceed that to start that motion there. And again, I've got my n already solved here. And then what I find then is the friction force is, again, a function of that p. OK, and step D, now I'm going to use my equilibrium equations once again. I'm going to sum forces now in the x direction. The right one, yep. Okay, so I just sum my forces in the x direction there, but note I've already solved for f of m. I'm going to plug that in. Time here. And what we'll see is then that's a function of p. That's got a p in it. So basically we've got one equation now in terms of p. And then just plugging and chugging along there. We've got that all in terms of p. We can solve for it. And what we find then is then to start motion up that ramp, p needs to be about 74.8 pounds. 70.4.9 basically. We'll start it in motion, and then it'll drop to that kinematic if we want to keep it going at a constant velocity there. We'll skip part D, and I want to go to motion down, because this is motion up. I'll again post that, but motion up is just simply putting in mu of k. So we'll look at part C, which is, I think, a little more interesting. And what p is necessary to keep the motion from going down. And again, what we're going to do is the same sort of thing, except that and this is where I say where the signs are a little bit different there. We're thinking now of letting it go down. So I've got my 45 here. I've got my P there. Normal force doesn't change. What changes now is going to be my F. And I'm going to take that to the maximum there. So what I'm going to do is figure out then what P is necessary to keep that from sliding down. Okay, so n doesn't change, right? The 45 and the p and everything, so I just simply sum those components in the f direction. So that's the same as before. Well, that's why we're not going to go through that calculation. Okay, basically the calculation for this is the same. What's going to be different, though, is that its direction is going to be different. And where that comes into play is then when we sum our forces in the x direction. So those first two components will be the same as what we did before. But now what's going to come in differently is that my f of m now will have a minus sign in front of it instead of a plus sign. But again, fm I solve for here, which is now a function of p. Plug those in. And what I find then is to keep it from sliding down, I need to have a P of 6.75 pounds acting on that.
Or anything more than that, between that and 74.
That's where I'm going with that. Now we've got our range. And that's what we're going to be looking at. Well, let's put it a better way. So the range that we want in terms of motion there is then our P needs to be between the 74.8 and the 6.75 for it to be in equilibrium. It's not going anywhere. If I exceed this, or if I go less than this, then it'll start moving down. If I go greater than this, it'll start moving up. So that's basically the range then of that P that keeps that particular block in equilibrium and keeps it from moving anywhere. You thoroughly confused? We'll take a quick look at the last one, the ladder problem. I'm not going to put it up on the screen so we can actually get through it and get you out of here. I know the weekend's calling.
Are you going to post this online?
Yeah, I'll post these, yeah. So, matter of fact, I'll just post them all online. So if you're having trouble getting them and that sort of thing. But that doesn't mean to stop writing and talking. Come on, guys. OK, now note, we've got this ladder, and we've been asked to find basically what the coefficient of friction is necessary to keep it in equilibrium. And it's 0 at this point B here. Which basically means it's a smooth surface. So what force should I be putting in there for that particular surface then? I'm taking that surface away from the ladder. Here's my ladder. As a matter of fact, I've got a weight here that'll be acting through the center. Normal force to the wall. Thank you. Well, yeah, normal, perpendicular. So that'll be our force B. There'll be a normal force at A there, so it's going to be perpendicular to that surface there. But the additional thing that we've got going on there is going to be our friction force. And then we've got some dimensions to throw in here. No, it's friction free, yeah. The 826 actually includes the friction. So yeah, be careful of that too. When you get into these problems, especially EIT, they'll throw things at you like one surface will be this, the other surface will be something else. So be careful of that. Make sure you think about it before you dive into it. OK, so we got some dimensions there. We're going to use our case. My pen's dying. Case 2.2, which is basically find that friction force, basically. I won't go through the explanation of that, but I think it's pretty obvious then that n is going to be equal to w in that particular case. OK, and then what we want to do in this particular category then is basically we're going to set it to that maximum friction force that's necessary to get that thing moving. Now, did this help us? No. Well, it's true. I mean, mu of s is equal to mu of s. That's a nice thing to know. OK, that didn't give us enough information. So what we want to do is then take a look at some other things that we can do. And one thing we can do is we haven't used all of our equations of equilibrium. We'll take moments about B. So we can set up a moment equation at B there, because I really don't care what B is. What I'm interested in is finding out this F. And what we can do is substitute in OK, we're going to substitute in for n. We're going to substitute in for f of m. And what we find then is that we end up having an equation just in mu of s. And then we can solve for that missing coefficient of friction.
That's unitless?
And that's unitless.